So today we're going to talk about more about polynomials. We're going to talk about finding the zeros of polynomials, building polynomials from the zeros, etc. So quick thing to recall, a lot of these words we're going to use mean the same thing, like roots or zeros or solution to when our function equals 0. They're also the same as the x-intercepts. Probably should have written that. Anyway, so the first thing we're going to talk about, we've talked about this a bunch before, the fundamental theorem of algebra. Pretty smart guy, this Carl Gauss. But his theorem basically says that any nth degree polynomial has exactly n zeros. They can be real, they can be imaginary, or they could be complex numbers. But if I've got some polynomial where x to the fourth is my largest degree, then we're going to have exactly 4 zeros, or 4, not necessarily x-intercepts because they can be imaginary, but there should be 4 zeros or solutions or roots when this function equals 0. Okay, so that highest degree tells us how many total zeros there are, and that does include repeats. Alright, so let's take a look at an example. Find all zeros of each function. And our first one here is x times the quantity x plus 3 squared. So when I want to know when this is 0, we're going to replace f of x with 0. And remember that x plus 3 quantity squared means that I have 2 of those factors. So go ahead and write those out. And then we set each factor equal to 0 using that zero product property. Either x equals 0, or x plus 3 equals 0, or the other x plus 3 equals 0. And of course, solving all of these, we end up getting that our 3 solutions are x equals 0, negative 3, and negative 3. Whoa. I don't know what happened there. Alright, so these are our 3 zeros. And if we take a look at our graph, remember we talked about multiplicity before at length. So when this repeats twice, it should bounce off the x-axis at that value. So at negative 3, it should look like it's bouncing off. Here's our graph, x times the quantity x plus 3 squared, and there it is at negative 3. It's bouncing off the x-axis and then passing through at 0, which had a multiplicity of 1. And again, so we can see that if we were to multiply all of our x's here, x times x times x, that would give me 1x cubed. That would be my leading coefficient if this was in that standard form. And so that also tells us about that end behavior, right? Odd degrees, so they're going in opposite directions. Positive leading coefficient, right side's going up. So lots of stuff to remember about that graph. Okay, let's take a look at our next example. Again, we're going to find the zeros. So we're going to replace this with 0. And so we're going to have x squared times x plus 2. And if you notice at the end, we have a difference of squares. So that factors into our conjugates x plus 3 and x minus 3. Okay. So to find all of our zeros, if we set x squared equal to 0, remember when we're solving that, we're taking the square root. But basically, also remember that this tells me there are 2 zeros hidden in this factor. Now we know here we would do plus or minus, and it kind of shows that there's 2 zeros there. But that's important. Whatever this number is will tell us how many zeros are hidden in that factor. So we get 2 zeros. So our graph should bounce off the x-axis at 0. We're going to get negative 2 from our next factor, negative 3 from our third factor, and positive 3 from our last one. So all in all, we have 5 zeros. And if we take a look, if we were to come back and multiply x squared times x squared, that's 1x to the 5th. So again, it's an odd degree polynomial. It should be going in opposite directions. Leading coefficient is positive. So we're going up and to the right. Should bounce off at 0 and pass through all these other ones. Let's take a look at our graph. And here it is. This thing's got a lot of stuff going on. But you can see it's starting from negative infinity, passes through at negative 3, passes through at negative 2, bounces off at 0, and then passes through at positive 3. Alright, our next example, this time we have some imaginary roots over here. So when we set these equal to 0 and use our zero product property, we still get x should equal -4, -2i, and +2i. Okay, so we have 3 zeros. 2 of them are imaginary, but 1 of them is real. So, and again, if I were to multiply these, x times x gives me 1x cubed. That would be my leading term if this whole thing was FOILed out. And so again, it's going up and to the right, and my tail end's going opposite directions, and it only passes through at -4. So if we look at that graph, here it is. I had to zoom out and change this a bit so we can kind of see what's happening on this part. But it does go up and to the right. I know the scale is really funky here if you look at it, but that is +4. +4. That's right, I'm sure some of you were yelling at me already. But it'll be alright. It'll be alright. But yes, there we go. Luckily I caught my error looking at my graph. Yeah, so passes at +4, right? The 0 there. And then we've got 2 imaginaries. So speaking about these imaginaries, let's take a look at our next example, which has some complex numbers in it. So we've got x plus 5 minus 3i and x plus 5 plus 3i. So this one looks like it's going to be harder to come up with those solutions. And rather than multiply it all together and then try to use something like quadratic formula, remember that all of our factors are in the form x minus k if f of k is a 0 of my function. So if k is a 0, all of our factors are in the form x minus k. So if I can get this in the form x minus something for each of these, then we can figure out what those zeros exactly are. So to do that, I want to kind of factor out a -1 from everything that's left. So a -1 from both of these terms. And if I do that, dividing both by -1, I get -5. And -1 divided by -3i is +3i. Okay, we're going to do the same thing over here. We're going to factor out a -1 from these two. That gives me -5 minus 3i. That's just going to change the signs of each of those inside of our remaining parentheses. So in this case, these are my k values. Beautiful handwriting. We've got -5 plus 3i and -5 minus 3i. And we can write that as -5 plus or minus 3i. Okay, so this particular graph doesn't cross the x-axis. My only 2 zeros are imaginary. And again, if I looked at x times x, that would be 1x squared. So this is a parabola where both ends are going the same direction, right side's going up, where both sides are going up. Now, if you actually took the time to multiply this thing all the way through, we end up getting x squared plus 10x plus 34. And you can see in this graph that here's my parabola. It never crosses the x-axis, and that's why we ended up with 2 imaginary solutions. Okay, so you probably noticed from those last 2 examples, or you might remember from last year, that imaginary or complex roots only come in conjugate pairs. So if a polynomial does have imaginary or complex roots, they only come in conjugate pairs. I.e., if -2i is a root or 0, then +2i must also be a root or 0. So let's apply that. Find a 4th degree polynomial function with real coefficients 0, 1, and I as its zeros. So remember, if it's 4th degree, we should have something that's x to the 4th in the end. So let's reconstruct some of our zeros. We know they're always in that form. I gotta stop doing that. X minus k, where k is our zeros. So I could write x minus 0, Or, of course, we could just write that factor as x, which will simplify it in a minute. X minus my next 0, which is 1. X minus I. But remember, if we have an imaginary or complex root, its conjugate must also be a 0. So negative I has to also be a 0. So x minus negative I really turns into plus a positive, or x plus I. Okay, so writing this so it's a little bit nicer, this really is just x, this is x minus 1, and this is x minus I and x plus I. Okay, and we want to multiply this whole thing together if we want that polynomial in standard form. So when you multiply, order's not important. That was not nice. Okay, but we're going to multiply our conjugates together first. Always do your conjugates together, so that way we can get those middle terms to cancel out. So remember, I only need to do the first term and last term. We don't need to worry about the middle terms with conjugates. That gives me x squared, x times x, and negative I times I is negative I squared. Gosh. There we go. All right, and over here we have x times x minus 1. But remember, I can replace I squared with negative 1. So minus negative 1 becomes plus positive 1. Okay. So my factor that gave me the two imaginaries is x squared plus 1. So let's go ahead and multiply these two together next. So x times x squared is x cubed. X times 1 is x. Negative 1 times x squared is negative 1x squared. And negative 1 times 1 is negative 1. Okay. And lastly, we're going to need to distribute this x that's out there through everything. And this should give me my x to the 4th power. So I'm going to do this a little out of order just so we can get to that kind of descending by power form in the end, or standard form. So x times x cubed is x to the 4th. X times x squared, negative x squared, sorry, is negative x to the 3rd. X times x is x squared. And x times negative 1 is negative 1x. So this should be my polynomial that has those zeros. If we take a look at our graph of this guy, there it is, x times x minus 1 times x squared plus 1. It does cross the x-axis twice at 0 and 1 and just passes through, but that's it. My other two zeros are imaginary, so it does not cross a 3rd or 4th time. Okay, last example. Find all zeros of this function and write as the product of linear factors. Okay, so this one we don't necessarily have to do that plus or minus p over q super long route. But what we can do, though, is treat this like a quadratic. This is kind of similar to, say, x squared minus x minus 20, which would be a quadratic that's factorable. And really, if this is true, and you did some of this last year, factoring things in the form of a quadratic, if this first term, like x to the 4th, so I'm just looking at the variable here, is the middle term squared. So if you take the middle term and square it, if that gives you the first term, which would be x to the 4th, then it is in the form of a quadratic. If we have like these nice 3 terms that looks like a factorable quadratic trinomial. So for instance here, if you took x to the 1st and squared it, remember when you raise a power to a power you multiply. So if you square this thing, this would be x squared. So we can actually factor this like it's a quadratic, but instead of x and x in there, we're going to have x squared and x squared. Let's see, this negative 20 tells me I have opposite signs. And the factors of 20 that subtract to 1 are 5 and 4. And to add up to negative 1, 5's negative, 4's positive. So let's see, this one is not factorable. There's not a difference of squares, or sorry, a sum of squares. There is a difference of squares, but it wants me to break this all the way down into its linear factors. So what we're going to do is finish finding our zeros. So we're going to set each of these equal to 0 and solve them for x. So here if I subtract 4, I get x squared equals negative 4. And then we take the square root. We get x equals plus or minus 2i. Okay, so there's two of our solutions. They're imaginary. Here I'm going to add 5 over. X squared equals 5, and take the square root as well. So we get x equals plus or minus the square root of 5, which doesn't simplify. So again, remember that if 2i is a factor, x minus 2i, sorry, if 2i is a 0, x minus 2i is a factor. And if negative 2i is a 0, x plus 2i has to be a factor. So these would be linear factors. They're x to the first power. And that's what it wanted me to do. Get everything down to the x to the first power. So same thing, if positive root 5 is a 0, x minus root 5 is a factor. And here would be my final factor. So this would be all linear factors. I know these are irrational numbers and these are imaginary, but we can still write it as the product of all of its linear factors.